Okay, this is observing exercise 2, and there's some challenging calculations here in part B, so I wanted to go through them. First of all, you have the sidereal day. It's given to you in hours, minutes, and seconds. So the first thing you want to do is calculate the period in just seconds alone. So here's how you would do that. You would take the 23 hours times 3600, 56 times 60, plus the 4.091, and that'll give you the number of seconds in a sidereal day. Then you'll use that to calculate the angular frequency. By definition, the angular frequency is 2 pi over the period, but you'll have to convert it over to degrees, first of all, by saying 360 degrees is equal to 2 pi radians. Then what you'll also need is that there are 60 arc minutes in 1 degree. That's because it says in the statement of the problem that we want the answer to be in arc minutes per second. The other calculation you'll need to do is to convert from the right ascension in hours, minutes, and seconds, first of all, to what is called decimal hours. The way you do that is you take the number of hours plus the number of minutes divided by 60 plus the number of seconds. This is the superscript S that we're talking about. This is just an example star, by the way, not the actual star you'll be observing. You'll take the 7 divided by 3600, and then you'll get a number which will be decimal hours. That's what goes here. Then to convert hours to degrees, remember that there are 15 degrees for every hour of right ascension, and that will give you the decimal degrees. You want to do the same thing for declination, except for declination is already in degrees, arc minutes and arc seconds. Those are different than minutes and seconds. So then you have the 1 plus the 2 divided by 60 rather, plus 3 divided by 3600, and that will give you a number which will be in decimal degrees. You probably want to use about 5 or 6 digits past the decimal over here. Then on page 2, recall that what we're doing is allowing the star to drift through the eyepiece field of view. So you center up the star, move it all the way to the right hand side, turn off the tracking, and calculate the time for it to go all the way through the center to the other side. So you don't want to make it go at an arc like, or cut off the circle like this. It needs to go directly through the center. It may take several minutes for that to happen, especially if you have a 26 millimeter eyepiece. Then what you'll do is you'll take 3 measurements, take an average of that. You'll go into this calculation right here, use the omega from the previous page, and this delta right here is the declination of the star. It makes sense that the time it takes for a star to go through the center actually depends upon the declination. So for example, if a star is near the equator, it's going to go through there rapidly, whereas if you have a star close to the North Celestial Pole, it'll take a very long time for the star to drift through the eyepiece field of view due to the rotation of the Earth. Then what you're going to do is compare that to the size, this will allow you to calculate the field of view size of the eyepiece, and you'll compare that to what the angular size of the moon is. And I believe that the moon just barely fits on the inside of the field of view, but you can verify that tonight with the gibbous moon. Hope that helps.